Yes, now we are going to look at the programming model for Simatic S7 1500. So it's again this chapter 4 here. Let's see if we can go to chapter 4, the programming model. A programming model, what is that? What is defined as the resources that the Simatic CPU offers for application programs. Application program is the programs you make to make things happen in the process that you want to happen, to control your process. So program elements that you can use, which are function and function blocks, and also tasks, but also data storage. So what we can have in this program model, there is a figure down here somewhere. I won't go through, but really quick. What you have is input data, which is information from your process to your CPU. Output data, which is information from the CPU to the process. Start a motor, for instance. First one is motor is running. You have got global memory, where you can store your information that you need to store temporarily or permanently or something as your program executes this. But global memory should be avoided. It's dangerous. In TI Portal, global memory is accessed by names, so it's a little better than it used to be in the legacy Simatic systems, but still they can be accessed from everywhere in your program. So if you intentionally write to global memory, you might destroy another program in your process. So it should be avoided as far as practical. Okay, then we have got static memory. There are two types. There's a program element called a function block. We get back to that. A function block has something called static memory. It's stored in a data block, the instance data block of the function block. And then we have also something called user data blocks, which is just data. They could be accessed from all programs, kind of global data, but they are stored in a block-oriented fashion. And then we have got local memory that you can use, and local memory is just read-write memory that's volatile. It's if you've written something in there, and the next time you want to use that information is either 0 or someone else has used your local memory and you don't know what's in it. So it's also called temporary memory. And then we've got data types in PLCs. Here are some of them. And you have in a PLC you've got a Boolean type, a bit type. It's normally now it's a Boolean type is a byte. It says if the byte is hexadecimal, 0x is hexadecimal, 00 is false, and 0xFF or something non-zero number, it's true. In older PLCs, a Boolean was a bit. There was just a bit in a byte. A byte is 8 bits. So there was just a bit in a byte. And then we got the byte type, and you have got something short integer type, minus 128 to plus 127. We got a word data type, which is 16 bits, double word, which is 4 bytes, and long word, which is 8 bytes, 64 bits, 32, 64. And then we got the integer or an unsigned integer. I didn't say an unsigned byte is 0 to 255, 254. And down here you got the unsigned integer, which is 0 to 65,000 something, and unsigned double integer is 0 to 4 million something, and signed is minus 2 million to plus 2 million half, roughly, and the long int is huge. We got time. Time is a number of milliseconds in 4 bytes. So time is basically a double integer variable, 0 to 24 days and something, since it's milliseconds. Long time is a little longer. That's let's say the number of nanoseconds. Usually since January 1st, 1990. And in nanoseconds, it can save something like, I think it's 500 years or something worth of time. You can say real, floating point, 10.0, for instance, 10.1. 10.0 could be an integer number, let's say 0, 1, 2, 3, no decimal places. Real, which is 4 bytes, and that's, I think the maximum number is 10 to the 39th or something like that. And long real, which is 8 byte, which is 10 to the 128th, to the power of 128, something like that. And then we have got constants. Constants, they are what they are. They constantly can't change. Most languages use 0x to denote hexadecimal. 16 hashtag is hexadecimal number. Here's a byte, and so on. Those are who you, the way you specify decimal. Then we have the coding elements. Now we've got the data and constants and whatnot, and then we need something to work on this data. Coding elements. So in a CPU here, we have got tasks. In Simatic, they are called organization blocks, and this is the link to your user program and operating system. And CPU contains various tasks, a number of tasks. They can be cyclic tasks running all the time, or they can be time cyclic to say, okay, every minute this task is going to execute, and the program you put into the task is going to be executed. Then we've got functions, and here are the programming language we talked about in an earlier video. Instruction FPD, ladder logic, or structured text, SCL is called in Siemens. Function block we have, and then we have a program, PRG. And the Siemens CPU does not support programs, so you can use an FC without inputs and outputs for this task. The difference between functions and function blocks is that a function block has static memory, which means that if the function block executes, is done and restarts, the memory that the function block saved is still there. A function does not have static memory. So that's the main difference. There's also another difference. A function only delivers one result, and a function block has a lot of outputs, can deliver a lot of results. Yeah, so that was quick. So here is the figure, the Simatic programming model. We have the operating system hosts tasks that we talked about. Each task called a program, but it could also call function and function blocks, which you could also write code directly in a task. You normally don't do that. A task called programs in the Siemens world, it would be a function without arguments, and the program organizes function blocks and functions, and the function blocks and functions, that's where you write your code. Of course, you have to write a little code in the tasks and the programs too to make something happen. Now, what you program here work on this memory that we talked about. It's input memory. That's information from your process, digital inputs, true, false, closed, open breakers, and transducers. Temperatures, for instance. Analog inputs. And then you have got the outputs here that you can communicate, because what your program does, read inputs, do whatever you are required to do, write to outputs. And the outputs, they are relay, for instance, or analog actuators, like frequency converters, which can control a motor from 0 to full speed. Yes, and then your program can also use data blocks. A function block has to use a data block, and so-called instance data block, where that's the data warehouse for your function block, where it saves its variables. There are also the inputs are stored there and outputs are stored there, and so on. And then you have user data blocks, which can be used by function blocks and functions and in tasks and whatever you want. They're kind of global. And then we've got this global memory that's accessible from all the programs in the CPU, like user data blocks. It's not protected, so it's a little dangerous to use. And then they can use local data. That's where you temporarily store something as you process your program from top to bottom. You need to save some data and read it back. Also for the model here is a little special. That's the input image and output image. That's memory in the PLC, and the gray here is on the input module, register in the input module. And what the operating system does for you says all these registers on your input modules are copied to this internal memory for fast access for your program. But if you have a name for a variable input number 1 and write :P, it says it should be the peripheral information I need, and then the operating system will go and read the register off of the module if need be. And it's the same for the output. You read to this memory, the operating system copies this memory to the output modules, or you can specify the :P and write directly to the module if need be. And the way this is being addressed is the name. They all variables, they are named variables, but internally the input said input image is an I, and the byte number and a bit number if it's a Boolean value, true, false. So then the byte number can, for instance, be 0. Or I. The percent says it's or percent input 0.2. That's the second bit in the first byte up here. Output is analogous, and memory is the same here. But if I write for instance percent I double U is input word, that would be just the IV and the I and the W and the number 0, for instance. A word is 2 bytes, so that would be byte 0 and 1, and it's the same out here. And the global memory over here has the M, so it's input, output, and memory. Here's a little, it shows a little example of this. So this input and output image has a little more details about this. I'm just going to talk about this figure. Here's the module, has register, a digital input module with 32 digital inputs, which is 4 bytes, 32 through 8 is 4. What the operating system says, the first byte is transferred into this input image, II, next byte afterwards, and so on and so on. So here are 4 bytes somewhere. There's a byte 0 offset. This offset is somewhere down there, maybe 120 or whatever. And you have a certain amount of this input image available here. Outputs, just the same. You write to these bytes, and the operating system transfers it to the open module. Here could be a relay, closing a contact, make current flow. And here could be a light switch or a digital input or something that sets the first bit to true or false in this byte. For analog inputs and outputs, it's a little different, because an analog input, a channel, this could be a temperature here, which shows just a current 40 to 20 milliamps, occupies 2 bytes. The operating system transfers this into the internal memory, but one channel uses 2 bytes. And here you have to be careful, because if this was the address x and x plus 1, one channel, the next one would not be, let's say if this was 10, there would be 10 and 11 for the first channel and 12 and 13 for the next channel. So don't use 10 for first channel and 11 for second channel, because then you get half of the first channel and half of the second channel. And the only thing that's, it's not going to be a correct value. Yes, outputs, just the same. A channel occupies, there are 16 bits, a word, and the operating system transfers it like this. And now, just as a brief one here, for inputs, Simatic, they have microprocessors or microcontrollers on the analog input module. So you get these numbers in this word that you have, which is an integer. Word is plus minus is minus 32, 768 to 32, 767 plus. But they don't use the full range. Yeah. And here is the way you address these. Then that was the input and outputs and how that work. And then we got the data blocks, and we have got instance data block for functions. So a function is your code, has the local data, you write your code there, and it works on this data, forgets that data, works on new data, and goes back and work on the first data, which means that a function block that you make can be used to control more than one equipment. If I make a function block to control an electrical motor, you can use the same function block to control 100 electrical motor through these instances. Motor 1 data, motor 2 data, motor 3 data, provided the motors are identical. Electrical motors. Yes. Yes. And then, of course, I don't have just one function block type. I have more function blocks, and they have their own instance data block. So these are roughly a class and instance data block. You make those instance data block, but would correspond to the new or whatever declaration you use in normal to make an instance of a code that you have written or class you've written. Okay, and those were the functions, no data blocks. And then we have got, when we talk about those data blocks, and this was special for instance data block, and then we have got the task organization block, and here are types: cyclic program execution, time control, interrupt control, and startup. The startup is really important because when you start a PLC, the PLC has to go out to the process that is controlling, check out what is the state. What is the state of my digital input, my analog inputs? And then your PLC must assume this state. So let's say the last time you controlled the process, a motor was running, and then your CPU stops, and then someone stops the motor, or maybe the motor stops because you are not controlling it anymore, but you remember, okay, it was running, and then you restart the CPU and just starts the motor. Not good, especially not after 14 days, if your process has been stopped for 14 days. So important. You can read. Function and function blocks. Here is the main difference. I talked about that earlier. What they have. Yeah. So here is how the function blocks were. Function block and function look. And graphically, they will look like this. You have got input data on the left-hand side, output data on the right-hand side, and you have something called in-out data, where you can read the data and write them back out. You have internally temporary data. For a function block, you have got static data. The function does not have this, so for a function that's crossed out. So what your code does is it works on these data, basically as it's a PLC. It works on input data, manipulate the output data, and something happens in the process. The motor starts, you get a feedback, the motor is running, we are all happy, everything is fine in the process. And the motor is running a pump, so the water is flowing, which might be another input to another function block that says, okay, it's water flow. And then the code in that function block works on the water flow and maybe transmit that water flow to an HMI panel, so you can see what water flow is. That's a function block. Here it says what they are. Yes. And then it was back to this instance data block, the data blocks. We could also use user data blocks, which is general. I think I mentioned that earlier too. But here is the function block. The function block has a code and a declaration. When you program this, it has a declaration of data. There's no real memory behind. You say, I just want these data. So when I make an instance data block, there are the declaration up here that is going to be instantiated or put into the instance data block, and your code is working on. And that's input data, input output data, or pointers if they're complex data types. We have output data and static data, and temporary data is somewhere else in the CPU. So you write a function block, and then you work or you code on the declaration that you have up here. And when it's making an instance data block, then the program would start to work, when you load the program, would start to work on the real data. Yes. Now this is the framework. This is how a function would look, how to program, because this is what we are going to do. A program and a task doesn't have this possibility. A function has a name and a type. A type could, for instance, be integer. The function adds two integer values and returns the value as an integer. I add 10 and 20 and returns 30. And these 10 and 20, they would be here in input declarations. We look back at input data to the function. And the return value would be output. But this is how they look. Now in TI Portal, this is graphical, so you can't see this. You have to right-click and enter this as properties. But if you export the program from your PLC, then you could read this stuff. And after begin, you write your code, and for a function, if it's not void, you don't need to write anything here. But if it's not void, it's a type, then you say the function, the name you have here, must be set equal to something, the result that you want to deliver out of your function. There's something called user data types that could be this output. And then if you say that your function is a user data type, a user data type could, for instance, be a data type that contains a boolean, a real value, and an integer value. Then you would have to assign all these values down here, and the function would return that user data type. Function block is not a type because the function block is a type in itself. Input output declaration, in out, static, the function could not do, and so on. See, there's not type here or void or something because it has a lot of outputs. And here is how you do this. Let's say just now in TI Portal, you can write it like this in TI Portal, but it's normally entered in a table. Input, output, in out, and static data only for function blocks, temporary data, and also constants. Constants are just something that's used in the program. So instead of a number, we can call that number something. So if I use the number 100, I could write % if that's what I'm referring to. And then it would be, for instance, if a real number CR% colon real colon equals 100, if that's what I'm working on. So that's the framework. So this is the programming model of basically an ISE norm CPU and a Simatic CPU. So that was a quick walkthrough through the compendium for the chapter, which has to do with the Simatic programming module, which is also valid or written a little valid for other types of PLCs. Let's say TI Portal or the Simatic CPUs does not have the program element called program. Other CPUs would. But what we looked at is variables, inputs and output data blocks, and a little on the tasks, what types of tasks we have. It's common to use what we call a cyclic task. That's a task that executes the program. When it's done, it restarts the program. Execute, restart, execute, restart. We looked at that, all the data, and then we looked at program element that we can program to work on these data. And we have functions and function blocks that we can program. And a function delivers one result and doesn't remember. It has a goldfish memory, doesn't remember anything. And then we have a function block that has static data that remembers data as long as the CPU is under power. As long as there's power to the CPU, the data are saved in static data. And they can also be made retain data. And retain, even if you switch off your CPU power and switches back on, these data are saved. And a typical use for retentive data is used for something called parameters. Those are something I want to start a motor or open a valve is a better example. And the valve uses 10 seconds to open, and I have to supervise this, and I say, okay, if it's not open after 12 seconds, there's an error, and that's a parameter. Because maybe I have another valve that opens in 5 seconds, and then I will say, okay, if it's not open in 6 seconds, it's an error. That's a parameter. And then for one of these function block instances, I write 6 seconds, another one 12 seconds, and when I switch off power to my CPU and repowers it, it would be nice if they came back up with 6 and 12 seconds, and not the initial value that I usually have that maybe was 30 seconds or something. So those would usually be retentive data.